welcome to this deep dive. It seems like you're interested in the brain and how it learns and how it comes up with new ideas.
Yeah, and
We've got On Intelligence by Jeff Hawkins.
yeah, and what's really neat about this book is that it kind of combines like a computer science perspective and a neuroscience perspective. So it's not just about the brain, it's also about like how can we understand the brain to maybe build intelligent machines.
So you're saying that to really understand intelligence, we can't just focus on the brain itself. We also have to look at how it might be replicated.
Exactly. And Hawkins argues that a lot of traditional AI research has kind of hit a wall because they've been focusing on just mimicking behavior without really understanding what's going on under the hood.
So instead of like just teaching a machine to do something, we need to figure out how it would actually learn to do that on its own.
Yeah. It's like, you can teach a parrot to say Polly wants a cracker,
Right.
but the parrot doesn't really understand what it's saying.
It's not actually thinking about crackers.
Exactly. And Hawkins thinks that the key to unlocking real intelligence lies in understanding the neocortex, which is the outer layer of the brain.
So what's so special about the neocortex? What does it do that other parts of the brain don't?
Well, Hawkins argues that the neocortex is basically a prediction machine.
A prediction machine. What do you mean by that?
It means that it's constantly making predictions about the world based on your past experiences. So it's not just reacting to what's happening right now, it's actually trying to anticipate what's going to happen next.
Okay, I see. So instead of just responding to stimuli, it's like actively trying to guess what's coming next based on what it already knows.
Exactly. And he has this really great example to kind of illustrate this point. He calls it the altered door experiment.
Okay, the altered door. I'm intrigued.
So imagine you walk through a doorway and everything seems normal at first, but then you realize something is a little bit off. Maybe the doorknob is a couple of inches lower than it usually is, or maybe the paint on the door is a slightly different shade.
I think I get it. It's not like I'm walking up to a door and thinking,
Right.
okay, is the doorknob in the right place? I just kind of notice that something feels off.
Right. Your brain has already made a prediction about what the doorway should look like based on your previous experiences, and when that prediction is violated, it creates a sense of surprise.
It's like your brain is saying, hold on, that's not right. That's not how doors are supposed to work.
Yeah. And Hawkins points out that this is happening all the time, even when we're not consciously aware of it. Our brains are constantly making and testing these predictions.
So you mean like when I'm driving, I'm not really thinking about every little movement I make. My brain is just predicting where the car needs to go and making it happen.
Precisely. Or when you're catching a ball. You don't have to do complex calculations in your head about the ball's trajectory. Your brain is using its past experiences to predict where the ball is going to land.
Okay, this is pretty mind-blowing.
Mhm.
So our brains are basically like these little fortune tellers trying to predict the future all the time.
Yeah, and that's basically what intelligence is, according to Hawkins. It's not just about being smart or knowing a lot of facts. It's about this ability to learn from the past and use that knowledge to predict the future.
But okay, how did the brain actually store all those experiences and use them to make predictions? Does it have like a giant filing cabinet where it keeps all our memories?
That's a good question, and it's something that scientists have been trying to figure out for a long time.
So what does Hawkins say about it? Does he have an answer?
Well, he says the brain doesn't actually store specific memories in the way we might think. It doesn't remember like every single door you've ever seen or every conversation you've ever had. Instead, it stores patterns.
Patterns, like the general pattern of what a door looks like, or how conversations usually flow.
Exactly. Instead of remembering every specific detail, the brain extracts the underlying pattern so it can apply that knowledge to new situations.
So it's like learning the rules of the game instead of memorizing every single move.
That's a good analogy. And those patterns aren't just for physical objects like doors. They can be for anything, concepts, relationships, even emotions. Anything our brain can experience.
So how does all of this help with prediction, though? How do patterns turn into predictions about the future?
Let's say you hear the first few notes of a song you know.
Hmm.
Even if it's being played in a different key, you can still recognize it, right?
Oh, yeah, for sure. Especially if it's a song I really like.
That's because your brain has stored the essential pattern of the melody. Hawkins calls this an invariant representation. It's like a blueprint for the song that's not tied to any specific set of notes.
So even though the notes might be different, the underlying pattern is the same.
Right. And it's those invariant representations that allow the brain to make predictions. It's not just reacting to the specific notes it's hearing, it's applying a general pattern to the situation.
This is blowing my mind. So it's like our intelligence comes from our ability to recognize patterns and then use those patterns to guess what's going to happen next.
That's the heart of it, yeah. It's not just about being smart, it's about being able to learn from the past and use that knowledge to anticipate the future.
I'm definitely starting to see the world differently now. But if all this is happening in the neocortex, I'm curious to know more about how the neocortex itself is actually structured. How does it create and store these patterns?
That's a great question. And it's where the structure of the neocortex gets even more fascinating. It turns out that the neocortex has a very specific organization. And within this structure, there is a particular area that plays a really important role in this whole prediction process. Hawkins calls it layer one.
Layer one, huh?
Yeah.
It already sounds mysterious. I can't wait to hear more about it.
So we've been talking about this idea of the neocortex as a prediction machine, right? Constantly building and refining its model of the world based on our experiences.
Right. But how does it actually do that? Like, what's the physical structure that makes all of this possible?
Well, the neocortex itself has a really interesting structure. If you imagine the neocortex as a vast sheet of cells within that sheet, there are millions of tiny columns all organized perpendicular to the surface.
Okay, so it's like a layer cake with millions of tiny little layers stacked on top of each other.
Kind of, yeah. Except in this case, the layers are actually columns standing upright. And these columns are like the fundamental building blocks of the neocortex.
So each of these columns is like its own little mini brain.
You could think of it that way. Each column acts as a mini processing unit. It receives input from other parts of the brain, and it sends output to other areas.
So it's like a whole network of tiny little brains all working together.
That's right. And Hawkins suggests that each column is actually a fundamental unit of prediction.
Wait, so you're saying each of these tiny columns is making its own little predictions about the world?
Yeah. It's like a team of experts all working together, each with their own specialized knowledge. Some columns might be focused on recognizing shapes, others might be focused on detecting motion, and so on.
So going back to that example of seeing a dog, different columns in my visual cortex might be voting on whether what I'm seeing actually matches their idea of a dog.
Exactly. And here's where the prediction part comes in. Each column isn't just responding to the raw sensory input, it's also receiving feedback from other areas of the cortex, including areas higher up in the hierarchy.
So it's getting information from both the outside world and from other parts of the brain.
Yeah, and that feedback from other parts of the brain that represents the brain's predictions about what it expects to see.
So it's like each column is getting a message from headquarters saying, okay, based on everything we already know, we think you should be seeing this.
Exactly. And if the actual input matches the prediction, great, everything's working as expected. But if there's a mismatch, like in that altered door experiment, that signals the brain that something unexpected is happening and it needs to pay attention.
There's like a little alarm bell going off.
Right. And those mismatches, those prediction errors, are actually crucial for learning.
So our brains are actually learning from their mistakes.
That's right. Every time a prediction is wrong, it forces the brain to update its model of the world.
This is really making me think about how we learn in general. It's not just about memorizing facts or being told what to do. It's about making mistakes and learning from them.
Absolutely. And this is one of the key insights from Hawkins' book. Intelligence isn't about being perfect. It's about being able to adapt and learn from experience.
But how do those predictions actually get communicated from one column to another? Is there like a separate prediction network in the brain?
That's a great question. And it leads us to one of the most interesting parts of Hawkins' theory, the role of layer one.
Layer one. Sounds intriguing. What's so special about it?
Well, the neocortex has 6 layers, and layer one is the outermost layer. It's kind of like the interface between the neocortex and the rest of the brain.
So it's like the gateway to the neocortex.
Yeah, you could say that. And Hawkins proposes that layer one plays a crucial role in communication and prediction because it's where a lot of the connections between different columns happen. It's like the internet of the neocortex, allowing all those little processing units to talk to each other.
So it's not just about what's happening within each column. It's also about how those columns are connected to each other.
Exactly. And remember those invariant representations we talked about, those stable, generalized patterns? Well, Hawkins suggests that layer one helps to translate those invariant representations into specific predictions.
Okay, I'm not sure I follow that. How do you go from a general pattern to a specific prediction?
Well, think of it like this. Imagine you have a general idea for a story, the basic plot, the characters, the theme. That's like an invariant representation. But you could express that story in many different ways as a novel, a screenplay, even a song. It's still the same story at its core, but the specific details will be different depending on how you choose to express it.
So my brain has this library of stories, those invariant representations, but it needs a way to translate those stories into different outputs, like movements, words, or thoughts.
Exactly. And that's what Layer 1 does. It allows those high-level patterns to be routed to different parts of the brain, where they can be turned into specific predictions for different actions or perceptions.
So layer 1 is like a switchboard, connecting different parts of the brain and making sure the right information gets to the right place.
That's a good way to think about it. It's this flexibility that gives the neocortex its incredible power.
This is making me realize that even the simplest actions, like recognizing a friend's face, involve this whole symphony of predictions and pattern matching happening in the brain.
Exactly. It's all happening below the surface, constantly and effortlessly. But of course, we're not perfect prediction machines, are we? Sometimes our predictions turn out to be wrong.
That's for sure. Like when I reached for my phone but accidentally grabbed the TV remote instead.
Exactly. So what happens when our brains make a wrong prediction? Does everything just fall apart?
I mean, our brains don't just like shut down when they make a mistake.
Right. They actually use those mistakes to learn and get better.
So it's like those wrong predictions are actually valuable in a way.
Exactly. Think of it this way. Every time your brain makes a prediction, it's setting up an expectation. And when that expectation is violated, it creates a kind of surprise signal.
Like, hey, wait a minute, that's not what I was expecting.
Yeah, and that surprise signal triggers the brain to pay attention and learn from the experience.
So it's like our brains are always learning, even when we're not trying to.
That's right. It's a continuous process of updating and refining our model of the world. And this learning process actually happens at the level of individual neurons and their connections, which are called synapses.
Okay, I remember learning about synapses in biology class.
Yeah.
But how do they actually change based on these prediction errors?
Well, it's a bit technical, but the basic idea is that synapses can be strengthened or weakened based on experience. So when a prediction is confirmed, the synapses involved in making that prediction get a little boost.
Like they get a gold star for a job well done.
Exactly. But when a prediction is wrong, those synapses get adjusted to be less influential in the future.
So it's like our brain is constantly fine-tuning its connections, making the successful pathways stronger and the unsuccessful ones weaker.
That's a great way to put it. It's like pruning a tree. You get rid of the branches that aren't producing fruit and you encourage the ones that are.
And all of this is happening without us even realizing it.
Right. It's all part of this amazing self-organizing system that we call the brain.
This is making me think about how we learn new skills, too. It's not just about getting it right the first time. It's about practicing, making mistakes, and gradually getting better over time.
Exactly. It's all about those prediction errors.
Yeah. And this brings us back to what we were talking about earlier, Hawkins' idea that intelligence isn't just about being smart or knowing a lot of facts. It's about this ability to learn, adapt, and make accurate predictions about the world.
Absolutely. And it makes you wonder, if we want to create truly intelligent machines, maybe we need to move beyond just programming them with knowledge. Maybe we need to build machines that can learn from their own experiences, just like our brains do.
Machines that can make their own predictions, learn from their mistakes, and constantly update their models of the world. That's kind of a scary thought, isn't it?
It can be, but it's also really exciting. Imagine the possibilities. We could have machines that could help us solve some of the world's biggest problems, like climate change or poverty.
But like you said earlier, it's important to think about the ethical implications, too. We don't want to create machines that are intelligent but lack empathy or compassion.
That's right. We need to make sure that any intelligent machines we create are aligned with human values and goals.
It's like we need to teach them not just how to think, but also how to care.
Yeah. And ultimately, understanding how our own brains work is essential for navigating this new era of intelligent machines. The more we know about ourselves, the better equipped we'll be to shape the future of intelligence in a way that benefits all of humanity.
This deep dive has definitely given me a lot to think about. We started with a simple question about how the brain works, and we ended up exploring the nature of intelligence itself, the future of AI, and even the ethical challenges that come with creating intelligent machines.
It's been a fascinating journey, hasn't it?
It really has. And to you, our listener, we hope this has inspired you to think more deeply about your own brain. It's an incredible organ capable of amazing feats of learning, creativity, and prediction. So keep asking questions, keep exploring, and keep those synapses firing.
And who knows, maybe someday we'll be having this same conversation with a truly intelligent machine. Until then, Keep on learning.